Hello, welcome back. I'm Jason. Today we're going to talk about the concept of an aqueous solution and how compounds dissolve in water. Now, I encourage you to not gloss over this because it's something we look at every day. You put sugar in a cup of coffee or water and it dissolves. We see it all the time. You put salt in a cup of coffee or water and it dissolves. If you put sand in a cup of water, nothing happens. It just sinks to the bottom. Why do some things dissolve and some things don't? You put a block of wood in water, nothing happens. See, we see this so often that it doesn't even occur to us that it's weird. Why does water why is it able to break down and dissolve certain compounds, but doesn't do that with other compounds? And then furthermore, we're going to learn in just a second that in some substances, when they dissolve, they go further than dissolving and they actually break down into their constituent ions, like sodium chloride. When it goes in, it dissolves down and what we call dissociates into the sodium ion and the chlorine ion. Right? So you have this soup inside of your salty water of sodium ions, which are charged, and chlorine ions, which are charged in the other way, negatively charged. Right? And so some solutions can conduct electricity when they have these ions, these charged species floating around in the water. Right? But other substances don't do that at all, even if they dissolve. Like if you dissolve carbon dioxide, which is actually soluble in water, even though it's gas, it's a little weird, but it does dissolve in water. But it doesn't break down into charges, right? It doesn't break down, CO2 doesn't break down into like carbon ions or something. So of course you dissolve carbon dioxide in water, it does not conduct electricity. So that's what we're going to be talking about today. What determines if something can dissolve or not? How does it actually happen? What does it mean to dissolve? And then to go further, why do some compounds dissociate into these charged species like salt does? All right, so to motivate this, we can do we can talk about some general concepts first. So we talked about the concept of here's your bucket of water or your glass of water or whatever. I guess I should have drawn this in blue because down here at the bottom you have your water, which we all know is our familiar H2O, right? And then in we go with the salt, which is sodium chloride, right? One atom of sodium, one atom of chlorine. Now, just to define some terms, whenever you have a liquid and you're dissolving something in the liquid or trying to, the liquid that you're trying to dissolve into is called the solvent, right? You'll often see that in the hardware store, like you go get a solvent, maybe to take the paint off of your house or something, or whatever, a strong solvent. Water, turns out, even though it covers most of this planet, is a pretty good solvent. Right? And the reason it's a pretty good solvent to dissolve lots and lots of things, and we're going to talk more about it in just a second, is because this water molecule is a bent molecule, which we've talked about in the past, and because of the way this is the oxygen and these are the two hydrogen atoms, right? Because oxygen is so good at attracting electrons, these little sticks represent sharing of electrons between these atoms. It's a covalent bond here. And because oxygen is so good at holding on to electrons, there's a lot more protons in the nucleus, and the way the electrons are distributed, it can pull these shared electrons a little closer to the oxygen. And because of that, it kind of lays bare the proton, which is inside of this hydrogen. So the water molecule is effectively charged. We call it a polar molecule. The oxygen part of the molecule is slightly more negative on average, and the hydrogen part of the molecule is slightly more positive on average. Now overall, from a distance, if you look far away, it all averages out, and so this is a neutral water molecule. But I'm saying if you zoom in real tight and you get up real close, this oxygen will on average be slightly more negative than the hydrogens because it hogs the electrons. Now that polar nature of water makes it really good at dissolving things, breaking things apart. I'm going to talk more why in just a second. So the water is what is doing the dissolving. It's called the solvent. And whatever you put into the top is called the solute. It's a little bit of a weird word, but it's called the solute. So that is what goes into the water. So if you're putting sugar in there, you would call that the solute. If you're putting sodium chloride, you put the solute. You put carbon dioxide, you would actually call that the solute. And whatever is doing the dissolving is called the solvent. So I want to consider three different situations, right? Let's try to break this down. We all have heard that you should be careful when you're taking a bath not to like have electricity around, right? You don't want to have a toaster when it's operating and throw it in the bathtub with you. You don't want to have a hair dryer and electrocute yourself in the tub. But it might surprise you to know that pure water, that means water that doesn't have anything in it, no minerals, nothing dissolved in it, nothing like that. Pure water actually does not conduct electricity, very well anyway. It's not, a perfect insulator. Nothing's a perfect insulator if you have a high enough electric field, but in general, water does not conduct electricity. It conducts electricity, or begins to, when things are dissolved in water. So when you open your tap, that tap water has all kinds of stuff dissolved in it, from the plant where it was made, to any additives, to anything it picked up through the pipes, any dissolved substances, metals, whatever, are in that water. So the pure water I'm talking about would be distilled water. If you take a bucket of water and you boil it on the stove, and so the vapor comes off, and then you collect that water vapor and cool it down. So everything that was dissolved in has stayed in the container. The vapor is pure water, and then you condense it down. Of course, you got to be careful when you condense it down through the pipes. You don't pick up anything in the pipes, right? But if you do it perfectly, theoretically, pure distilled water will have nothing dissolved. It will be just H2O. Right? And so that does not conduct electricity. So we're going to take 3 different cases, right? The first case, like this, right? I'm going to label this pure H2O. And that's what I mean by pure H2O. Pure H2O, pure water, does not conduct electricity. So we're going to say it's not conducting. And what do I mean by not conducting? What I mean is, if I put an electric circuit that runs through this water, right? Like if I put a wire in here and another wire right here, I don't know, you could make like a, like some kind of like tab here or something like that if you want to. And if I connect this up to some kind of voltage source like this, I could put a light bulb here if you want to see if the light bulb's going to light up, or you could have a current meter or whatever, but some kind of voltage source, right? This could be a 9-volt battery, it could be anything. Right? Then no electric current will flow, or very, 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 very little electric current will flow, right? Because you can really never get totally pure water, you see, but in general, it should not conduct electricity. So let's take this situation and go a step further. What if we take another situation like this, and of course I'll have my water. Of course I closed off my top. That doesn't make sense. So it's open like this. So this is no longer pure water. This is water plus sugar. Regular old table sugar. So we all know that sugar dissolves in water, right? And what is sugar, by the way? Sugar is called sucrose. By the way, there's many flavors of sugar. There's fructose, there's sucrose, there's all kinds of slightly different chemical formulas that all taste a little sweet. But the one I'm talking about here is a large molecule, 12, C12, H22, and then 11 oxygens. And these are all bound together. They're covalently bonded together, or they're covalently bonded together, which means they're sharing electrons, and they kind of hang together as a grouping. That's called a covalent bond, or a molecule, something that hangs together as a unit, okay? Now you pour that in there, and it begins to disappear. Now when you're kids, you think it literally disappears, but then you learn when you get a little bit older, it doesn't disappear. What happens is the sugar molecules begin to separate from each other, and they end up fitting between the water molecules. So it seems that it disappears, but really all the sugar is still there. They just exist as each individual molecule between the water molecules, and so you don't see it anymore because it's so spread out. But it's all in there. It's just between the water molecules. Now, if you do the same thing, if you connect this thing up to a circuit like this, then what you're going to find out is the same thing. It's not going to conduct electricity. It's not going to conduct electricity. Okay? And that means that we have a word for it in chemistry. It's called a non-electrolyte. Non-electrolyte. Now, you've probably heard this word electrolyte before. When you get a sports drink, usually they're telling you, drink your electrolytes. Everybody needs their electrolytes. Okay, well, because your body runs on ions, a lot of it. Your nerves fire because of imbalances in ions. There's ions crossing the cell membranes like all the time. So yes, we get a lot of our minerals and things in the form of ions. And so when you drink that and it's got all that stuff in there, then supposedly it does good stuff for you and it helps your body when you're exercising. But in chemistry, when we talk about electrolyte, I'm not talking about a sports drink. I'm just talking about a substance that when it goes into the water, even if it dissolves, when I'm talking about if it's an electrolyte or not, I'm asking, does it break down into ions? Right? And in the case of sugar, it doesn't. What it does is these are molecules. It doesn't break them down into like oxygen ions and carbon ions and hydrogen ions. They all stay together as a neutral molecule, and they still exist between the water molecules, but it doesn't break down further. And so this is called a non-electrolyte. Doesn't break down, or it doesn't ionize. I'll say it that way. Because it does break down in the sense that a sugar cube, if you drop a sugar cube in water, the cube disintegrates, it breaks down. But all that's happening is the individual molecules are spreading out among and breaking down and separating from one another, but the molecules themselves are not splitting apart, they're not ionizing. And so because of that, this does not conduct electricity, right? Because you don't have any charges in here. Remember, what is electricity? It's the movement of electrons or the charge carriers in a wire. But electricity is broader than that. If you have a plasma like the solar wind, you have negative electrons flowing, but you also have positive protons and ions flowing around too. So electricity in general can be either positive or negative charges moving around. But in the solution of water, even if the sugar dissolves, if there's no charges in the water, there's no way for the electrons, when they come out of this battery, how are they going to get from here to here? There's no way to do it because this is essentially a giant insulator. And what I'm saying is sugar behaves the same way because it doesn't break into ions. All right, so let's go to the final one, which you already know the punchline, but we're still going to say it all out loud because, learning things is like a series of repeating things over and over and over until you build a model in your mind, at least for me. All right, so inside of here, we're going to have a mixture of water plus sodium chloride. That's the famous example, but there are lots of things that dissolve in water that will allow electricity to conduct. So if we do this one, right, if we connect this one up to a circuit like this, and, we can put a light bulb here if you want, right, that's my little light bulb, something like that, then, these electrons are going to attempt to go through the light bulb. They're going to light it up, they're going to go into solution, and this sodium chloride behaves differently than sugar. It dissolves the sodium chloride, but it goes further and it breaks apart the sodium from the chlorine in the water. But the sodium doesn't exist as a neutral sodium atom, it goes into its ionized form, sodium ions. And the chlorine doesn't break into its neutral atom, it goes into chlorine ions. And so you have sodium charges and chlorine charges, ions, floating around the solution, and that facilitates the electric current to be able to flow in a circuit. And so you would see the light bulb illuminate here, whereas you would not see it illuminate here, and you would not see it illuminate here. So let me get all this written down here. So this will conduct, I'll say does conduct. And when I mean conduct electricity. And it dissolves, just like the sugar dissolves, but it goes further, a step further. It also dissociates. A long time ago, when I learned chemistry the first time, I thought dissociation meant dissolving. And I was confused for a long time. But actually, dissolving is different than dissociation. You can think of dissolving as step one. Step one is you have to break you put wood in water, it doesn't even dissolve. You put sand in water, it doesn't even dissolve. But sugar does dissolve. So that's step one. It has to break it all down and get everything to fit between the water molecules. But step two is to take that substance and physically rip it apart into its constituents. And that is what is happening here. So what ends up happening, it dissociates into the sodium ion, not the neutral form of it, but the charged form of it, and the chlorine ion, which is negative right here, right? And these ions are electrically charged. So I'm going to talk a little bit more about what happens for the electrical conductivity in a second, but just remember from the periodic table, sodium lives in column 1, So in general, whenever it bonded with chlorine in the first place, it wants to lose an electron to look like the nearest noble gas. It loses an electron, that makes it positively charged. Chlorine loves to gain electrons to look like argon, so it would love to gain an electron. So the sodium loses its electron, gives it to the chlorine, but in that state, whenever that electron transfer has happened, then those atoms, that's what they want to do, and those atoms then like to live as ions because chlorine is an electron hog. It grabs electrons, and sodium, that outer electron is just not as strongly held on to. So remember, atoms don't have personalities. They don't really want to do anything. I don't really like using that word, but it's the only word I can come up with. The reason sodium loses its electron is because that outer electron is just not held on as tightly by the nucleus because there's only one electron. We're going to talk about electron orbitals and shells later, but there's only a lone electron way out far away from the nucleus. It's just not held on. It's like Pluto. It's just not held on very strongly. And the way chlorine is constructed, it has a very strong attractive force to based on its nucleus of positive charges and the surrounding electrons. It can grab another one very strongly. And so those two like to party because one likes to lose and one likes to gain. All right, so because of this, it conducts electricity, and because of this, we call it an electrolyte. Because it has dissolved ions and it breaks into ions. So the word electrolyte in your mind means that not only does it dissolve, but it also dissociates. And when something dissociates, it breaks into ions. That's what electrolyte means. So an electrolyte is a solution, or an electrolyte solution is a solution that will conduct electricity, right? Even if something dissolves, it does not mean it will conduct electricity, just like sugar does not conduct electricity because it doesn't break down. So then you have to ask yourself, well, why do these two behave differently? And that's really what the rest of this lesson is going to be about. But I'm going to give you kind of the overview punchline now, and then I'm going to talk in a whole lot more detail why these two things behave differently. Right? The main reason why is because this is an ionic compound, and this is a covalent molecule. Remember what the difference is. Sodium is on the left-hand side of the table, chlorine is on the right. When you have something on the left and on the right, or a metal on the left with some negative polyatomic ion, and they bond, it's an ionic bond. That is a transfer of electrons over from one to the other. And so you have very strong charges. The sodium loses an electron, the chlorine gains an electron, and then they're oppositely charged, which means there's a very strong attraction of electric attraction between opposite charges, all right? And because water is also slightly charged, we talked about it being polar, it's able to break it apart because those strong charges are there. That's the reason, okay? Sugar is a much more complicated molecule. You would think it would be so much easier to break this down. But look at carbon is on the right side of the table. Oxygen's on the right side of the table. Hydrogen is technically on the left, but hydrogen's weird and it behaves mostly like a non-metal on the right. Even though we put it on the left because it's atomic number 1, it behaves mostly like a metal on the right. It wants to gain an electron most of the time. Sometimes it can lose an electron, but most of the time it gains an electron, and it wants to share electrons in order to do that, and so that's covalently bonded. So this is covalently bonded, and it's a molecule, and there are little charge imbalances across this molecule that help it dissolve, but there are no very strong ions inside of here, like there is inside of this one, because we transferred the electron from sodium to the chlorine. Everything is shared as far as electrons go here. So there could be slight charges across the molecule, like water is a molecule also, and it's polar. There could be some slight charge imbalances across, which helps it dissolve. But there are no strong charges inside of here that would allow water to rip it apart. So it's not able to pull it apart, so it doesn't dissolve into ions, and so it doesn't conduct electricity. That is the difference between electrolytes and non-electrolytes. And that's why some substances break down and others don't. Most ionic compounds, I'll talk more in just a second, most ionic compounds, when they dissolve, they further dissociate into ions. Most molecules are not going to be electrolytes. They're not going to be able to break down into ions, so they won't conduct electricity. All right, so the rest of what I'm going to talk about here is exactly how water is able to do this, the details. Right? And so we've talked about a lot of it in the broad strokes, but I want to go just a level deeper to make sure that we all understand. How does dissolving happen? Well, we have this water molecule. It's a bent molecule, and so there's an oxygen and then there's 2 hydrogens. And just as I have held this up before, it more or less looks like this, H2O, right? Now, as we are going to learn about a little bit later, oxygen, because it's on the right-hand side of the table, is very, very good at attracting electrons. You know, on Earth, almost everything oxidizes. You know, lots of reactions happen with oxygen. Any burning is a reaction with oxygen. That's because oxygen is really good at grabbing electrons. And why is it really good at it? Well, it goes into the details of how many protons are in the nucleus and how the electrons are surrounding the atom. There's a leftover propensity for the nucleus to pull in more electrons. And I'll talk about that more when we get to electron configuration, but that's basically why. It's the force that that nucleus has is able to grab more electrons very easily. Anything on the right-hand side of the table close to the noble gases are able to do that for reasons we'll talk about later. So this is much, much better at grabbing electrons. The hydrogen is just a single proton and a single electron. But it also, according to the periodic table, it's on the left, it wants to look like helium. It wants to have 2 electrons to fill its shell there that we'll talk about a little bit later. So the way that this water molecule does it is one of the oxygen atoms begins to share the electron from the hydrogen, and the hydrogen shares here. So each of these lines represent 2 electrons, not 1, 2, which exist kind of between, and they're equally shared, except that's not the right word. They're not equally shared. They are shared among the 2 atoms, but this one is better at pulling in electrons. So this electron cloud gets pulled a little more to the oxygen, and this electron cloud gets pulled a little bit more to the oxygen. And because of that, oxygen looks like slightly negative charge. Don't worry about this weird snake thing. This is a Greek delta. It's just a Greek letter to represent something. In this case, we're representing charge. It means the oxygen's slightly negative. And then this hydrogen is slightly positive. This little sigma or this little delta means slight charge, which is positive. And this is slight charge, which is positive, because if I'm able to pull the electrons a little closer, then this proton that's in the center is exposed a little more, and so it's slightly positive. Also crucial to this is that it's a bent molecule. Because it's bent, then the positive nature of the hydrogens are down below, and the negative nature is up above. We're going to talk about why water is bent much later, but it has to do with the electrons that surround the atoms and how the electron configuration works, which we have to get to later. But water is bent, which means the oxygen's negative part kind of sticks out one way, and the hydrogen's positive part are down below. Okay? Now, when we talk about water, we write it down as H2O, but you need to start thinking about water looking like this, because this will describe why things happen. This is just a shorthand way of saying, oh, this is what it is. But this, it will describe and help us describe why things happen all the time. Now, a couple of notes here. These electrons here, these are covalent bond, because water is a molecule, right? And that means the oxygen is slightly negative, and the hydrogen is slightly positive. I've already said those things in words. But overall, when you zoom out far, far, far away, the positive and negative nature of this molecule, they all add up, and so, or they algebraically add to 0. So water is a neutral molecule. It's just that when you get right up on top of it, part of it looks positive and part of it looks negative. And it's always like that. It's a permanent dipole is what we say. Permanent polar character of water. All right, always like this. All right. Now, as we mentioned, this is a molecule. We talk about molecules mostly. Let me get my periodic table back out. Normally we say ionic is when you have a left-hand side bonded to something on the right-hand side, or a left-hand side bonded to a polyatomic ion like sulfate or something like that, nitrate polyatomic ion. And a covalent molecule are usually when you have 2 elements on the right-hand side of the table, like CO2 or nitrous oxide or whatever. I could go on and on. Things that are on the right-hand side bonded together are usually molecules, and they're sharing electrons. But hydrogen's the weird one because it's printed over here. I want you to think of hydrogen mostly behaving like a non-metal. Think about it. It's a gas. It doesn't look like a metal. But it's on the left because it's element 1, and occasionally hydrogen can behave kind of like a metal in certain situations. But most of the time, like in water, H2O, it's behaving like a non-metal, which means it's sharing electrons, right? And so water is a covalently bonded molecule. But I also want to, you know, when I was in chemistry, I learned that there's two kinds of things. There's a thing called an ionic bond, when the electron is transferred, like sodium chloride. And then there's a covalent bond, where electrons are shared, like water. And that's true, but I also want to put the bit in your mind that ionic bond and covalent bond mostly exist along a continuous spectrum. It's like a spectrum. In other words, if you think about bonding between atoms being a sharing of electrons, like in water, it's a sharing of electrons. That's what the black lines mean over here, a sharing of two electrons. There's two of them here, and they're both being shared, kind of in the middle, hanging out in the middle. So that's in general what molecules like to do. But the extreme form of sharing is if one person took it all. I mean, in other words, in this case, it's not shared equally. Oxygen gets them a little more of the time. It's like child support, you know? You have two parents, and you would think that both parents get them equal amount of time. However, let's pretend the wife gets the kids, you know, all 5 days of the week, and the dad only gets them on the weekends. Okay, so that's unequal sharing. But what if the wife got the kids 99.9% of the time, and then the father got the kids like 1% or 0.1% of the time? It would still technically be sharing, but the wife would have it all the time. And so you might as well say it's transferred, I guess is what I'm trying to say. Like if you're in child support situation and you're getting the kids 364 days of the year, and I'm getting them 1 day a year, technically we're sharing, but I've got the kids so much, or the wife has the kids so much, that you might as well just say the kids have been transferred to the wife. And that's what I'm trying to say. Okay, because I want to talk about this as more of a continuum. It's a little bit of an advanced topic, but I think it's kind of nice to talk about it in the beginning. We say that sodium chloride is ionic, that the electron is transferred. And we say that sugar and carbon dioxide and water and nitrous oxide and some of these other molecules are covalent, which means sharing of electrons. But I do want you to think of electron behavior as a continuum. Most of the time, or a lot of the time, they are shared in the terms of a molecule that sticks together as a unit. But if you share more and more and more and more and more, such that the electron eventually is living on the other species like almost all the time, then it's effectively transferred over, and that's what ends up happening in the case of an ionic bond. So the nature of bonding is not like one or the other. Is it ionic or is it covalent? When you get into chemistry more, you realize that it's a whole gradation. Which species is able to hang on to those electrons more often? And if one species is hogging it all the time, we just go ahead and say it's ionic, and then the electron is transferred over, right? But it is a continuum. Chemistry doesn't know about our dumb definitions, right? We have definitions, we put it into buckets. But there are lots of compounds that live in the middle where they're equally shared, and there's some compounds that live on one side where they're not shared so much one direction, and then there's lots of compounds where it's shared the other way, and then there's other compounds where it's shared so much that we might as well just say the electron gets transferred over. And in the case of sodium chloride, with sodium and chlorine on opposite sides, we basically say the electron's transferred over, and that solid that is left behind when we make sodium chloride consists of sodium ions and chlorine ions, and they're always like that because the electron is effectively transferred over. So when it goes into water, what's going to be able to happen here is this sodium is positive and this chlorine is negative, and sodium chloride is a lattice. It's a crystal structure. You can look at the crystalline nature of it. You can look at it under a microscope, and it's a regular repeating pattern of sodium chlorine, sodium chlorine, sodium chlorine, but they're ions. They're not neutral atoms. They're ions. They're charged. So as soon as you put that into water, the negative side of the water molecule is going to be attracted to the sodium, which is positive, right? And the positive side of all the water molecules are going to be attracted to the chlorine, which is negative. And they're going to be pulling and tugging on that whole lattice if you drop a sugar cube in and pulling it apart. And not only just pulling it apart into sodium chloride units, they're going to be able to rip apart the sodium and chlorine bond altogether. Now, why is it able to rip it apart? Well, that just means that the pulling that's going on, or the force from the water molecules, is stronger than the inter-ion force of the sodium chloride that's bonded together. So one force is stronger than the other. That's why it dissolves, right? So if you ever in chemistry want to know why something happens, it almost always is just because the force of one thing was stronger than the force of another thing. The force of all those trillions of water molecules pulling on that stuff, and remember, from all different directions. because if you have a sodium ion in the middle surrounded by 16 water atoms or water molecules, then they're all going to be pulling from different directions, and it's going to separate that stuff out. And that force happens to be stronger than the force holding the sodium and the chlorine together. Okay, and in the case of this, where there aren't very strong ions here, the water is still able to separate it into molecules, because usually electrons are like a cloud, okay? Electrons are not like a ball that goes around. I mean, that's what we learn when we're young. But they're a probability cloud. They're more like a fuzzy cloud than anything else, all right? I can't tell you exactly what they are because nobody knows exactly what they are. That's the truth. But they behave kind of like a fuzzy cloud. And so that means in a big molecule like this, there can be charge imbalances that are shifting around like all the time. It's like a fuzzy little thing going on. And so some of this molecule could be slightly positive and negative, and it switches back and forth very often. So the water can still separate it, but there are no strong positive and negative ions inside to rip it apart, so it doesn't dissociate. That's because this is molecular and not ionic. So the ionic compounds tend to dissolve, and further, they tend to dissociate because they have strong charges that are inside the lattice of what that ionic compound is. Whereas molecules like carbon dioxide, there may be slight charge imbalances that allow it to dissolve, but there are not strong charges like sodium and chlorine, and so it can't be ripped apart. That's why the molecules in general don't dissociate, but some of them do dissolve. All right? So to bring that home a little bit, I want to say, let's say that in solution, we have the sodium ion and we have the chlorine ion. Why does that happen? Well, when we put the salt crystal before it fell into the water, these were connected together physically because this is a positive charge and this is a negative charge, and they were bonded together, very, very strong ionic bond, okay? But as soon as it goes into the water, you have all these polar water molecules floating around. And so what can happen is, since you can have a water molecule with oxygen here, and this is hydrogen, and this is hydrogen. Remember, oxygen is positive. It's very slightly positive, and it's going to be attracted to this, so that's why it goes this side down. And then another water molecule could be on this side, and this is slightly negative also, attracted here. But then you can have one over here, and one over here, and one on the back side, one on the front side, and it completely surrounds this sodium ion with oxygens, essentially. And the similar thing is happening over here. For the chlorine atom, you can have the H2O arranging itself like this because the hydrogen is very slightly positive, and it's going to be attracted to the chlorine. And then you have the same thing here, hydrogen right here, and this is the bent molecule right here. These are positive attracted to negative. And you can have one here, and one here, and one here. So the reason salt dissociates in water is because of the polar nature of water and of the high charges on the sodium and chlorine ions, because it's ionic, right? And because of that, the water molecules surround and rip it apart, and then once you have it ripped apart, the water molecules literally surround the ions, and when it's surrounded like this, prevent them from coming back together. So it doesn't really recombine very much back into sodium chloride because water molecules are surrounding both species. That's why it disappears when we stir it. It seems to disappear because it's getting in between the water molecules. Now this sugar, or other things like carbon dioxide, they can also dissolve. They can break down from bulk form and fit between the water molecules, but they don't get ripped apart, right? So they don't conduct electricity. So I've talked a lot about sodium chloride because we have a lot of experience with that, and I've talked a lot about sugar because we've had a lot of experience with that. But let's take another compound. Let's take something called sodium sulfate. We're going to do a lot of talking about different compounds, but let's just pick one for now, sodium sulfate. So Na2SO4. Now, is this ionic or covalently bonded? Well, it's a metal on the left-hand side of the table. If it were a non-metal, we would know it's ionic, but this is a polyatomic ion, which can behave as a unit, which is negative. And so we still say this is ionically bonded. Positive charge on the sodium, negative charge on the sulfate. All right? So we say that this is ionic. right? And because it's ionic, when it goes into solution, the water molecules are going to surround this thing, and this is going to be a positive charge inside of this compound here. So the negative side of the water, the oxygen side of the water, is going to be attracted to this and start pulling on it. And the hydrogens are going to be pulling on the sulfates, and it's literally going to dissolve it and then rip it apart. And so it's going to break down into sodium ions as ions in aqueous solution. And it's going to break down into sulfate ions, whoops, which has a charge of -2 on the sulfate ion in aqueous solution. Now we're going to write actual equations a little bit more clear in just a bit. So I'm not trying to write an equation. I'm just trying to tell you that this species is going to break down, but it's not going to break down into neutral sodium. It's going to break down into the ion because this thing's bonded together. It's an ion that is attracted to the sulfate ion, and so they're bonded together. So when they get ripped apart, it gets ripped apart into sodium ions, and this gets ripped apart into sulfate ions. So in solution, you would have charged species running around, sulfate ions, sodium ions, and so that solution should conduct electricity, all right? So then what I want to do, this is just another example. I want to summarize the rules of thumb I want you to have, and we're going to talk more about them in the next lesson as well. Most water-soluble ionic compounds are strong electrolytes. If you have to remember one thing for this lesson, that's what I want you to remember. Ionic compounds, most of them dissolve in water because of the charged nature of ionic compounds. And further, the ones that do dissolve in water are all strong electrolytes. I'm sure there's an exception out there, but for what we're doing right now, we can say that that's going to be true. So I'm going to write that down. And this is something important. So most water-soluble ionic compounds are strong electrolytes. And what I mean by strong electrolytes is I mean they completely break down into their ions. And so it's an ion solution, and so it conducts electricity. That's what this means, right? And then to go a step further, just to put it into words before I write it down, most molecules, which are atoms that are covalently bonded from the right-hand side of the periodic table, or also including hydrogen behaves mostly as a nonmetal as well. Most molecules are not going to dissolve in water, but some do, like carbon dioxide does, right? There's some that do dissolve in water, but in general, if you look at like the millions and trillions of molecules out there, most of them are not going to dissolve in water because they're just not highly charged, okay? They're sharing, and there's not super highly charged parts of that molecule there to be able to break it down, not going to dissolve in water. And even the ones that do dissolve in water, in general, don't dissociate down to their ions. Now, there's a big exception I'm going to tell you in a minute, but in general, that is the case. So the way that we're going to write this down is we're going to say most molecules, right, are not electrolytes. And most aren't soluble. But some are. I mean, there's always exceptions. Most molecules are not electrolytes, and most of them don't dissolve in water. But there are exceptions. Sugar is a molecule, it dissolves in water. Carbon dioxide is a molecule, it dissolves in water. And I can go on and on with other ones. I'm going to talk about methanol in just a second. Methanol is a molecule, and it dissolves in water. But in general, even when they dissolve in water, they do not break down. Molecules generally do not dissociate into their ions. And the reason is because there's just not very strong charges in a molecule. There's shared electrons, not transferred electrons, and so there's not very strong charges for the water to grab and pull them apart. It might be some charge imbalances to help break it down, but pulling it apart, that much force to pull it apart, there's not enough force to do it because there's not enough charge imbalance on a molecule, most molecules, to do that, with some big exceptions. So let me talk about those real quick. Methanol, right, which has a chemical formula of CH3OH. Now there's a structure to this, but this is how we write it down, you know, in the shortest form. This does dissolve, right? But it's a non-electrolyte. And what this basically means is that this behaves as a molecule. This is a nonmetal. This is a nonmetal. Hydrogen, we always consider to be a nonmetal, behave like a nonmetal. So this is a molecular sharing, covalently bonded there. And there is some charge imbalance. This, especially on this side, when you say CH3, you have carbon in the center and hydrogen's coming off of it. Okay, so remember, hydrogen doesn't hold on to its electrons very good. Carbon is not as good as oxygen at grabbing electrons, but it does pull them a little bit. So there's a little bit of a charge imbalance here from the electron sharing from the hydrogens to the carbon. And so water, the surrounding water, is able to pull on those and separate the methanol molecules down. But this charge imbalance that is here, it's not super strong like sodium chloride. It's not like a transfer of electrons, so it's just not strong enough to break it apart, so it doesn't dissociate, so it's a non-electrolyte. And then we also talked about, in passing, CO2, carbon dioxide. It's the same kind of thing. It dissolves, but it's also a non-electrolyte. What's the commonality between these two? They're both molecules. So in general, if they're a molecule, they can sometimes dissolve, but even if they do dissolve, they're not going to be an electrolyte. And also, I've chosen examples where they dissolve, but there's many molecules. Most of them don't dissolve there. Now, there's one big example, a counterexample to the general rule that most molecules don't dissolve. And that big, huge, very important counterexample is acids, right? Acids. We're going to talk more about acids very soon. And we have talked briefly about them in the past. But acids basically are molecules. So molecules shouldn't dissolve, right? But acids do dissolve. And when they dissolve, they release their hydrogen ions. And an acid is a substance with lots of hydrogen ions in solution. Right? Hydrochloric acid, sulfuric acid, they all have hydrogen in there. So you can think of acids being hydrogen ion donors. And that's what they are. So they break down and they violate the rule because I told you hydrogen's a little weird. It is technically a nonmetal, but it behaves differently than the other nonmetals. And so it's on the left-hand side of the table, but it's not really a metal and it's just a little weird. So that's why it's part of this exception. All right. So let me talk about acids, or let's talk about hydrochloric acid, HCl. Is this a molecule or not? Well, this is on the left-hand side of the table, but I told you it behaves more like a nonmetal. So nonmetal, that's a molecule, right? So it's a molecule. So you would think it would not dissolve and it would not be an electrolyte. However, when you put it in aqueous solution, it actually breaks down into hydrogen ions, right? And chlorine ions. And an acid is any substance that's a hydrogen ion donor. When it breaks down and has lots of hydrogen ions in there. That's what an acid is. The more of these that are in there, the stronger the acid. So that super corrosive acid from like Alien that can like melt through, you know, metal decking all the way down to the end of the ship, that must have a lot of hydrogen ions in there to do that. So the water molecules surround this and it's able to pull them apart. It's the main exception. It's technically a molecule, but it does dissociate. So there's counter examples to everything. And by the way, I can't resist just telling you, why do acids, we're gonna get into this a lot more later, but why do acids react so violently with things? Why do we think of acids breaking down things? Well, it's because this hydrogen here, an acid in general is a hydrogen ion donor. So if there's a lot of these in solution, you have a lot of, what is a hydrogen ion? Hydrogen has one proton and one electron. So if it's an ion, the electron's gone. So it's literally just proton. One of the strongest forces in nature is the electric attraction between charges. It's much stronger than gravity, millions of times stronger than gravity. So if you have a single proton just floating around, which is what this is, you could relabel this hydrogen ion to proton if you wanted to, and it's just sitting in solution. That means anything you put in solution, it's going to want to steal the electrons and react with it. Because it's just a bare proton, nothing shielding it. It's just hanging out, ready to suck in any electron it sees, even from an electron cloud, from a metal, or whatever. So if you put zinc in with this hydrochloric acid, there's lots of electrons at the outer edge of the zinc atom, and it's going to rip one off immediately and begin to react with it and form hydrogen gas and all these other things, because it's so, it's just a bare proton, and it can very easily suck in another electron. So that's why acids react. Okay, so in general, we're going to go through a turbo run of this. So we have this thing called a solution. It consists of a solvent, which is the liquid, and the solute, the thing that you try to dissolve in there. Pure water does not conduct electricity because there's no charges in here. So if you hook a circuit up, no electron flow will happen. If you put sugar in, it does dissolve, but it does not conduct electricity, right? And that's because the sugar doesn't break down further into ions. And so if you hook a battery up here, no electric current will flow. But if you put sodium chloride in there, it will conduct electricity, it does dissolve, and it does what we call dissociate, break down further into its ions. So it's called an electrolyte. An electrolyte is a substance that breaks down into its ions. A non-electrolyte is a substance that doesn't break down into its ions, even though they both dissolve, okay? And it conducts electricity because of this. Now, the details of how the electrons get to the other side is actually kind of complicated with these ions. You have a negative terminal of this battery here, so the positive sodium will be attracted there, that's in solution. The positive terminal of this, the chlorine will be attracted, and then there's electron transfer and some chemistry going on there I haven't gotten into, but that's why the circuit can function. You have to have charges in solution. Now, how does the charges actually occur? How does the breakdown occur? Well, it comes down to water being polar. Because of the electron sharing, the oxygen slightly negative. The hydrogens are slightly positive, right? And because of that, they can surround the sodium chloride, break it down, and then rip it apart. Because of the strong ionic character, it's attracted to the negative nature of the oxygen, and when it's surrounded like that, it can just literally separate it like that. But in the case of sugar, there's no strong charges in here. There could be temporary charge imbalances in the gigantic electron cloud that's here, but no strong ionic charges to rip it apart, so it doesn't dissociate, even though it dissolves. Same thing happens with chlorine surrounded by the other end of the oxygens, and that or other end of the water, and that's what keeps them from recombining. All right, another example of an ionic compound, sodium sulfate, would break down into sodium ions and sulfate ions. So the general rule of thumb is most water-soluble ionic compounds, and most ionic compounds are water-soluble, there's some exceptions, but if they're soluble in water and if they're ionic, they are strong electrolytes. That's what I want you to remember. And also, most molecules are not electrolytes, and most of them are not soluble in water, even though I gave you counterexamples in this lesson. Most of the time, they won't dissolve in water. Most of the time, they will not break down, even if they do dissolve in water. Methanol, for example, does dissolve, but does not break down, so it's not an electrolyte. Carbon dioxide does dissolve, but it doesn't break down, so it's a non-electrolyte. Now, the big exception to this is hydrochloric acid. This behaves as a nonmetal, covalently bonded to a nonmetal, so it's a molecule. However, it does dissociate. That's because hydrogens is a little weird. And then we talked about acids being proton donors or hydrogen ion donors. That's what a strong acid is. The more of those you have, the stronger the acid is. All right, I hope that we have broken down the seemingly everyday common sense behavior of dissolving into something that we understand a little bit deeper. Now, what I'd like you to do is go through this again, make sure you understand. And then in the next topic, we'll talk a little bit more about the difference between strong electrolytes and weak electrolytes and how to write the dissociation reactions down to more accurately describe exactly how the dissociation happens. Learn anything at mathandscience.com.